Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. We have done a part of the chain growth polymerization for the introduction last week, and now we proceed with the chain growth polymerization in free radical. Now we look at the lesson outcomes first. At the end of this subchapter, students should be able to list the free radical initiators, write the decomposition of the initiators, list the suitable monomer for free radical polymerization, explain briefly the inhibition and retardation, and write in details the mechanism for free radical polymerization. Now we look at the introduction first for the free radical polymerization. As we learned last week about the homolytic and heterolytic, and the initiation of the free radical reaction actually is usually depend on unimolecular homolytic dissociation of the weak bonds by the irradiation or by the presence of the heat. The free radical polymerization was categorized based on the type of initiators used in the reaction. The initiator used were free radical initiator. A free radical is an atomic or molecular species whose normal bonding system has been modified such that an unpaired electron remains associated with the new structure. And the radical is capable of reacting with an olefinic monomer to generate an active center chain carrier. The presence of the initiator such as the organic peroxide, for example, benzoyl peroxide, azo compound such as 2,2 bis azo butyronitrate readily will be dissociated first to form a free radical. So, in general, ion may be produced when the double bond monomer are subjected to electrophilic or nucleophilic attack, and it will form a Lewis acid such as boron trifluoride in an anionic or cationic polymerization. We also have a Ziegler-Natta catalyst, which is in the coordination polymerization by reduce the transition metal oxide on a support, such as the aluminium oxide and alphine catalyst. The general structure of radically polymerizable monomer in chain growth polymerization must contain double bonds. So the general formula is CH2 double bond C double bond Cr 3 Cr4. So R is H, which is hydrogen. R usually substituents that stabilize the growing radical. And this monomer is susceptible to attack by free radical, by ionic initiator to form the active center. And in chain growth polymerization, monomer together with the initiator will form the monomer together with the initiating species. And the initiating species that attach the monomer, we call it as the growing center or active center. And based upon the growth center, the chain growth polymerization, we can classify into free radical, ionic, and also coordination. This one is type of the monomer together with the R4. So R4 might be H, hydrogen, benzene ring, CN, COO, CH3, and so on, depends on the monomer. And this monomer will then produce a polymer. So monomer that are not susceptible to free radical addition is CH2 double bond CH 1 2 3 4 5 6. Monomer we call it as 1,2 alpha olefin, whereby it polymerized to oils only. This one is the triglyceride, one of the triglyceride structure of the oil. For example, the sunflower oil, which is organic or natural sources of the polymer. So this monomer is not susceptible to free radical addition. This one also methyl vinyl ether, also not susceptible to free radical. And also 1,2-disubstituted ethylenes. An effective, we look at the initiator. An effective initiator is a molecule which, subjected to heat, electromagnetic radiation, or chemical reaction, will readily undergo homolytic fusion into the radical. So the free radical, which is the radical with the active center, may be produced when a labile organic compound, which is the initiator, is decomposed by heat, light, or particular radiation. For example, if we have a styrene or methyl methacrylate, when this monomer is heated, free radicals are readily formed. So this radical must stable long enough to react with monomer and create an active center. Free radical initiators can be classified into four major types. We have peroxide, hydroperoxide as a compound, redox initiator, and photoinitiators. First, we'll look at the peroxide and hydroperoxide initiators. Commonly used peroxide and hydroperoxide is benzoyl peroxide, or also known as the BPO. It is thermally unstable initiator. It dissolves in the organic solvent and easily decomposes into the radical. The rate of decomposition depends on their structure and on the temperature. Of course, the initiator must be decomposed first for it to be in the first step of the chain growth polymerization, of the free radical polymerization, which are the initiation step. So before the initiation step, the initiator must decompose first. So BPO, the rate of the decomposition is depend on the structure. And the organic peroxide compounds are generally used for polymerization in bulk and suspension. Inorganic peroxide compounds are the most suitable for polymerization in solution and emulsion. List of some peroxide and hydroperoxide compounds that generate free radical is given in table 3.2. Now we look at hydrogen peroxide. This is the structure for the hydrogen peroxide. Suitable temperature for polymerization lies between 30 to 80 degrees C. We have potassium peroxide disulfide, dibenzoyl peroxide, cumene hydroperoxide, and dilute butyl peroxide. Decomposition of peroxide and hydroperoxide. Decomposition occurs when the single bond between the hydrogen is break up to form a radical. We look at the structure of the hydrogen peroxide. We have HOOH. So one of the bond here is break up for it to form a radical, and it will become HO with the active site here plus the OH with the active site. This is the decomposition step of the initiator. Okay, another example for benzoyl peroxide. This one is the structure of benzoyl peroxide together with the benzene ring. We have COO, CO, and benzene ring. After decomposition at 60 degrees C, it returns into CO and CO. Okay, we have two CO, right? If you don't want to produce or write 2CO, you can write C double bond O together with active site plus C double bond O benzene ring together with active site. Now we look at the cumyl hydroperoxide. The double bond, or not double bond, the breakup of the bond is here. Okay, so it will produce CH3 plus with OH. Low dissociation energy of the OO bond, but reagents are unstable. So we rarely use cumyl hydroperoxide. Now we look at the azo compound. It is more stable than hydrogen peroxide or peroxide and hydroperoxide. So it is stable at room temperature. And azo compound may be decomposed at low temperature by ultraviolet radiation, and it decomposes thermally above 40 degrees C or photochemically below 40 degrees C, giving substituted alkyl radical and liberating nitrogen. Azo compounds are especially suited as initiators for polymerization in bulk or in organic solvent. And the yield of the free radical is not quantitative because of the cage effect. So the cage effect is the primary recombination and the secondary recombination of the free radical. So hence, the efficiency factor may be used to show the effective radical concentration in this reaction. Okay, now we look at the example of the azo compound. So mostly and widely used is AIBN or azo by cis azo bis isobutyronitril, AIBN, which is the temperature for this AIBN to decompose at 50 to 70 degrees C. We have 2,2-azo bis 2-amidinopropane and 2,2-azo bis gynopentanoic acid. The most widely used is AIBN, and the structure is more easily to recognize. The decomposition occurs when the bond between the carbon and the nitrogen break up to give the nitrogen gas. So this one is the structure for AIBN. So the breakup of the bond is happening here between N and N at the double bond here. And this double bond will be transferred to produce CH3C, CH3CN with the radical plus with the N2 and plus with another CH3, CH3 and CN. So we have two structure for CH3C, CH3CN. Now we look at the redox initiator. So redox is the reduction and oxidation reaction which describes all the chemical reaction in which the atoms have changed their oxidation number. And the production of free radical by one electron transfer reaction rates are easily to control by varying the concentration of metal ion or peroxide. Redox initiator can be processed at relatively low temperature with high rates and with formation of high molecular weight polymer. It is usually carried out in aqueous solution, suspension and emulsion polymerization, which is water as a solvent or dispersion. And the table here shows some of the example for the oxidizing agent and the reducing agent. So we have the hydrogen peroxide as oxidizing agent, peroxo disulfide, hydroperoxide, and so on. And for reducing agent, we have Ag plus, Fe2 plus, and so on. Amine, hydrogen sulfides, The combination of the oxidizing agent and reducing agents are suggested for this purpose.